The next reaction that we're going to talk about is a Friedel-Crafts acylation. Now, an example of a Friedel-Crafts acylation is shown here, okay? And what we're seeing is an H atom on the aromatic ring is replaced by an acyl group. Now, right here, when we talk about the acyl group, which I added an extra E in, so let me back that up. What we're really talking about there is either an R or an H with a C double bond O. And so when we do this, it produces an aromatic ketone, which is shown here. Now, a Friedel-Crafts acylation is carried out much in the same way as a Friedel-Crafts alkylation, except the aromatic species is treated with an acid chloride, which is also sometimes called an acyl chloride instead of an alkyl chloride. So let's look at this mechanism. So much in the same way, we're going to start with aluminum chloride. And then we are going to draw our other group. And so what we see here is that the aluminum chloride is a strong Lewis acid catalyst, and the electrons are from the chlorine are going to come here and attack that aluminum through a coordination reaction. Right, now through this coordination reaction, we get, I'm double checking my charges. I was missing a charge on aluminum. We get this complex here. Now this will undergo heterolysis, right? Oop. I got really wild with my arrow there, so let me go back. This will undergo heterolysis. To give us these products. Okay, now this here is called an acylium ion, and it is a relatively highly reactive electrophile, but it is resonance stabilized. Okay, and so you can draw the resonance structure here. At this stage, now we go through electrophilic addition. Where these electrons come in and attack the carbon at that positive charge. And what we see here and I'm just looking back and forth and counting my bonds. Because I'm always trying to double check, and you should be too. And what I'm specifically trying to double check is there's 1, 2, 3 carbons here, and this is going to make a new bond right here, and so there should be 1, 2, 3 carbons. And so as I go from step to step, that's one of the things I do that's just a really nice double check, because it is so easy to forget one of those carbons. And so we just always want to make sure that we're checking our work as we go along. All right, so now we're here, and remember we've got an H, and I just talked all about checking my work and I left out some bonds. So let's put those in. Okay, so we've got a hydrogen there, and what's going to happen is just like before, The chlorine here, the electrons that make up this bond between the chlorine and aluminum are going to come here and they're going to drag that proton back. And then these electrons are going to go right here. These electrons are going to go right here, right? And reestablish the aromaticity. And there we are. So we finally get our aromatic ketone product. Let's talk a little bit more about that acylium ion and its resonance structures. So it might seem weird that the Friedel-Crafts acylation can take place at all, because that chlorine atom in the acid chloride reactant is bonded to an sp2 hybridized carbon, which we had just talked about prevents the Friedel-Crafts alkylation from taking place. But this acylium ion is really the key. It's resonance stabilized by the lone pair of electrons on that adjacent oxygen atom here. And so with that additional stability, the cationic electrophile can be produced and enter the aromatic substitution, electrophilic aromatic substitution ion. So the fact that this is resonance stabilized allows this reaction to go. Now, unlike Friedel-Crafts alkylation reactions, right, Friedel-Crafts acylation reactions are not susceptible to carbocation rearrangements. We don't make a carbocation here, so we don't have to worry about that. The acylium ion is not going to rearrange because its positive charge is already delocalized by resonance, and because it has a resonance structure in which all non-hydrogen atoms have an octet. So I misspoke there. It does form a carbocation. It just doesn't, because it's right there next to the oxygen, it doesn't, it's resonance stabilized, so it will not react. The Friedel-Crafts acylation reactions, however, can be used with a variety of acyl halides to produce different aromatic ketones. But one of the things we have to be careful of is that a Friedel-Crafts acylation as a mean of formylation, replacing the hydrogen by a formyl group, requires the in situ formation of the very, very unstable Cl-CH double bond O. So a few things to think about there when we are looking at these particular reactions. Now, the next reaction we're going to focus on is nitration. I want to point something out here. The reaction after this is sulfonation, and it's also going to have nitric acid. So I want to point out and make it really clear before we get there. If HNO3 is the only reactant, it's going to be nitration. Okay, so basically what happens here is one of the hydrogen atoms on the ring is replaced with a NO2 group. Okay, and so that's a nitro group. So let's look at this mechanism. Okay, so we're starting out with our nitric acid there, right? And I've drawn it out for you here. And then I'm going to kind of do a truncated nitric acid just to help save us with space here, okay? And the first thing we're going to see is a proton transfer reaction, where these electrons come in, they're going to grab that proton, and those electrons are going to go on the oxygen. Okay, then right, what we're going to see here are that these electrons are going to go there to form a double bond. And then that water is such a good leaving group. It's an excellent leaving group, and so that's going to leave. Okay, and so this is a heterolysis step. So then what we're going to see here right, is a nitronium ion. And this is what goes through the electrophilic addition. So those electrons come and they attack that nitrogen on the nitronium ion, and then these electrons jump back up on the oxygen. Now, I just happened to choose the top oxygen there, but we understand that these are three-dimensional molecules, and so if you had chosen the bottom one, that also would be fine. Positive charge there. All right. Sorry, I'm just double checking everything before we undergo our next step, which is the electrophilic elimination. And that water that we generated acts as a base and will accept that proton, right? And then these electrons go here to form that double bond. And then this is our final product. We've reestablished aromaticity. Right? And we can draw the nitrate as the NO2 like you saw on the previous page, or we can also draw it out like this. Now, you can, let's talk a little bit about this. So I have messed up. And so I need you to think, to erase what I said before, because I got confused because I didn't have it written in my notes until this page. Sometimes you see, let me put it here. This is the one that is mixed. Sometimes you will see sulfuric acid with nitration. Okay. Whereas the sulfonation, you see sulfuric acid by itself. So I apologize profusely for that. So what happens here is if you just use nitric acid alone, this tends to proceed really slowly. The rate is slow because the amount of NO2 plus that can be made here the amount of NO2 plus that can be made here is just really small. It's about 4%. And so the rate of the electrophilic aromatic solution is directly proportional to the concentration of this electrophile. So the more concentrated you make, the faster the rate's going to go. So to increase the rate of nitration, the reaction can be run at really high temperatures. The other thing you can do is add the sulfuric acid, because that sulfuric acid, which has a pKa of about -9, is much more acidic than nitric acid. So when the sulfuric acid acts as the acid, a substantially higher concentration of the electrophile is generated. So again, I apologize. I flip-flopped it on the previous slide. Sometimes you're going to see sulfuric acid with nitration, right? And so you just need to be aware of that. If you see sulfuric acid all by itself, then it has gone through sulfonation, which is shown here. So this is sulfonation, where a hydrogen is replaced with a sulfo group, and that is spelled a sulfo group like that, which is SO3H or SO3R. And so let's look at a sulfonation mechanism. So when we look at the sulfonation mechanism here, right, there's also sulfuric acid, and just like before with the nitric acid, I'm going to draw a kind of shortened version of the second molecule of sulfuric acid. Right, and the very first thing, just like before in the nitric acid one, is a proton transfer. Okay, and so there's our proton transfer. And through this, what we're going to see here is this form, and then it's going to undergo heterolysis, where these electrons are going to come here. And then water is such a great leaving group. It's very, very stable. Okay, and so then there we have our ion, and this is the part where it's going to go through electrophilic addition. And during this electrophilic addition process, right, these electrons are going to come out and they're going to attack that sulfur, right? And then these electrons are going to come back up here on the OH. And I messed up with my number of electrons here. So let me go back and fix that. There's only one pair of electrons there. Yeah, so I got excited and drew in extra electrons. I'm just checking to make sure everything else I drew was fine. Okay, so that undergoes the electrophilic addition. And then what we're going to see here is this group. And then there's a positive charge here. Now, this is when it undergoes an electrophile elimination, where water comes in, right, and steals that proton, drags it back, and then those electrons go there. And so now we have added our sulfo group. So this is the kind of last of the big five of the EAS reactions. Now let's talk about the rate of sulfonation. As we saw with nitration, sulfonation can be slow because the concentration of the HSO3 plus electrophile in concentrated sulfuric acid is rather small. So sulfonation can be sped up by using fuming sulfuric acid, which is concentrated sulfuric acid that's infused with SO3 right here. Okay. And under these conditions, SO3 can also be protonated to produce HSO3, right, according to this equilibrium. So that is one way to speed up the rate. Now, although most of the electrophilic aromatic substitution reactions we've looked at are generally irreversible, sulfonation is an exception. Sulfonation is reversible through a process called desulfonation. Notice that water is a product of the sulfonation reaction, and so if you treat the arene sulfonic acid, which is this guy here, with large amounts of water, under slightly acidic conditions, you can remove that sulfo group and get your benzene back. So it is reversible through this reaction.